All right, this is Honors Algebra 2 Pre-Calculus. We're doing 4.7 in Pre-Calc, which is inverse trigonometric functions. So let's do a quick review of how inverse functions work. Recall that to have an inverse function, a function must pass the horizontal line test. And when a function doesn't pass that horizontal line test, we sometimes use a domain restriction to make it have an inverse function. So, for example, f of x equals x squared, you can see fails the horizontal line test, right? A horizontal line goes through it twice, right? So it doesn't have an inverse function, but we can cheat and we can say, hey, let's only look at this graph from 0 to infinity, right? Which would be essentially half of the graph that would pass the horizontal line test. Now you could also pick the other half, we just commonly pick this half. And if I put this domain restriction on it, then what's going to happen is I'm going to end up with this green inverse function, right? F inverse of x is going to be the square root of x, and that so notice that this graph had a domain of 0 to infinity, right? Because we put that restriction on it. And it also had a range from 0 to infinity, right? And so this is not possibly the best example, but what's going to happen on your inverse function is the domain and the range switch. The reason I said it wasn't necessarily the best example is because here the domain and range are the same, so you don't really notice that they switch, but I assure you that's what happened, right? Cool. So that's the basic idea. Now, let's go ahead and move forward with this. So due to the periodic nature of trig functions, they can't have inverse functions without domain restrictions, right? Because every trig function we've seen is going to fail the horizontal line test. So what's important here is that we're going to have to put a domain restriction on the original function, and that will become the range restriction on the inverse. The reason that's important is that when we use inverse sine and cosine and tangent buttons in our calculator, which are over here, and we'll talk about them soon, when we use those, we're only going to get one answer out, like a specific answer that falls in the range of that inverse trig function. And it's going to be on us as the people actually using the information the calculator gives us to logic out what that means about the actual other solutions, because there will be others sometimes. So that's why it's important to get the domain and range. So what we're going to do in this section, first I'm going to walk you through, not spend a ton of detailed time on it, but I want to walk you through the 6 inverse trig functions and show their domain and range so that you know what they look like. Then we're going to spend some time using the inverse trig functions in a calculator. We're going to learn how to find the other 3 inverse trig functions because they don't have buttons in the calculator. And then we're going to talk about how to find angles given values on the unit circle with no calculator. And then we're actually going to do one more that I forgot to put on here, which is we're going to talk about taking algebraic stuff, or we're going to talk about taking arc trig and writing it as an algebraic expression. And I meant to put that number there and I forgot. So there you go. All right, so let's start with sine, right? So this is the graph of sine x in red, right? But I've restricted the domain to be from negative pi over 2 to pi over 2, right? So you can see that this is one section, the piece that was in green here that I just highlighted in purple. That section is the section that we're going to find the inverse for. So the restricted domain for sine is negative pi over 2 to pi over 2. Now, why does that make sense with the unit circle? Remember that sine is the y on the unit circle. So since sine of theta is the y on the unit circle, by starting at negative pi over 2 and going up until pi over 2, I've hit every possible y value. That's the reason it has to be that window. I have to hit every possible, so this hits all of the y values on the unit circle. It hits the lowest one at -1 and goes all the way up to the top one at 1, right? So this is what our inverse function looks like. Just like we saw that the range of the original sine x was from -1 to 1, the domain of the inverse sine is -1 to 1, and the domain that was restricted in order to have an inverse sine was negative pi over 2 to pi over 2. Well, now that makes this the range of this function. And you're really not going to have to graph these very often. Knowing the domain and range is mostly helpful in this sense right here, so that you know that if you find the inverse sine of something, the answer your calculator is going to give you is going to be in this window, and we'll talk about that more in the video. So here's our cosine. Now you'll notice if you think about this in terms of the unit circle, right, cosine is the x on the unit circle, right, x in the unit circle. So in order to hit every possible x, I'm going to start at 0 and go to pi. Now there are other windows that would also do that, but sort of the way to think about this is all of these intervals either include 0 or start at 0. So here, this interval was around 0, right? And the reason that this was not a 3 pi over 2, the reason it's a negative pi over 2 is that 3 pi over 2 would not be consecutive around 0, right? Like, if you wanted to go from pi over 2 to 3 pi over 2, you'd have to go this way, and that's not what we want, right? We want negative pi over 2 up to pi over 2, right? So here the window we have is 0 to pi, and you can see that that hits every x value in the unit circle, so that's why that's our window. So that's our domain restriction, which means that that's going to be the restricted output you're going to get for cosine, is from between 0 and pi, and you can see that the range and domain switch as well. All right, so for tangent, we're going to take this tangent that's in the middle, right around 0, which goes from negative pi over 2 to pi over 2, not included, because if you notice, there's an asymptote at pi over 2 and negative pi over 2. And notice that tangent goes up and down forever. Well, that means that an arctangent is going to go left and right forever. So the domain of the arctangent is negative infinity to infinity, and the range is between the pi over 2's, negative pi over 2 and pi over 2, but again, exclusive. You can't actually include the pi over 2. All right, so let's keep going. All right, so cotangent's the same basic graph as tangent, but it looks like a negative x cubed instead, right? Notice that on this one, our window is going to be that 0 to pi again, right? So I'm basically catching one of those tangent lines, right? Because there's a bunch of tangent curves, or cotangent curves, my bad. So here we picked one of them, right? And it was the one right around 0. Here we're also picking one of them, and it's the one that starts right by 0. So 0 to pi, not included again, right? Because there's asymptotes at 0 and pi. And just like we saw with tangent, the range was negative infinity to infinity, which means that'll be the domain for my arc cotangent or my inverse cotangent. So secant and cosecant, the trick is I can't just take the top u because that would fail the horizontal line test, right? And I can't take the whole bottom u because that would fail the horizontal line test. So what we end up doing is we end up taking the interval again from 0 to pi, which you've seen before, but skipping the vertical asymptote. So see how there's a vertical asymptote at pi over 2. So the domain is essentially, if we look at this graph, right, it goes from 0, which is included, up to pi over 2, but that can't be included, jumps over pi over 2, and then goes all the way to pi, right? And that makes sense because remember, secant of theta is 1 over the x on the unit circle, so I have to hit all the x's. It's going to have to go this way to hit all the x's, but it can't be this one because that would be a vertical asymptote, right? And again, you'll notice that this thing had a range of negative infinity up to negative 1, which we can see here because it's negative infinity up to negative 1, and up here it's 1 to infinity, right? So that's my range on the original, which means it's going to be the domain on the inverse, right? So that's how that works. And then we'll go ahead and look at cosecant. So for cosecant, again, cosecant is 1 over the y value, right? 1 over the y value. So I need to hit every y value. Well, that's going to be that same window from negative pi over 2 to pi over 2. But again, we have a vertical asymptote when y on the unit circle is 0. So it's going to be negative pi over 2 to 0 and 0 to pi over 2, skipping over that 0 because the vertical asymptote. And again, you can see the domain and the range switch. So basically, the short version is all of your trig functions, right? So if they, if you look back for a sec, so sine and tangent and cosecant, they all use this window. Now some of them you include the endpoints, some of them are missing. So sine uses this window, right? Tangent uses this window, but with open dots at the end, right? So tangent uses the same window, but with open circles at the end, right? And cosecant uses the same window, but with that vertical asymptote in the middle, right? So that's what they all look like, and then the other ones, right? So cosine and cotangent and secant, right? They look like this. They use the top window, right? So cosine uses 0 to pi, right, with closed dots, and cotangent uses 0 to pi, but with open dots, right? And then secant uses 0 to pi with closed dots on the end, but an open dot in the middle because there's a vertical asymptote. So it's really one of those two sets of the unit circle that you're looking for answers on. All right. And I think, so let's go ahead and talk why this is useful. So primarily, this informs you, basically, it tells you what info you can get from your calculator and what info you can't. So your calculator only gives you the output that falls in the range of the inverse trig function. If you're asked to find values in, let's say, 0 to 2 pi for that equation, you're going to have to use your logic. After your calculator gives you an answer, you're going to have to logic it out and figure out the other value. So, for example, let's say I want to know all the values in 0 to 2 pi such that sine of theta equals 0.237. Now, I should check my mode. I'm pretty sure I'm in radians. Yeah, okay. So I want to know when sine of theta is 0.237. Well, the way I'm going to do that is I'm going to type into my calculator inverse sine. So I'm going to basically take the inverse sine to get rid of sine, and I'm going to do inverse sine of 0.237. So I'm going to go ahead and do that. So let's do inverse sine of 0.237. Great. Okay, that's my answer. So I'm going to go ahead and get theta, and I'm going to call it theta 1 because there's going to be another one, is 0.239 ... but I'm going to store that as a because I think I'm going to have to use it again. So I'm going to store it as alpha a. So here's the problem. I know that I'm looking for a sine value, right, that there's a positive 0.2 something, right? So that's probably somewhere like here, right? That's, oh, I didn't mean to, hang on. I thought I hit store A and I didn't, so I just entered what the old A was. Sorry, store alpha A. There we go. All right, cool. So that's here, right? That's this theta 1, right? But there's another value because the sign is the y on the unit circle, there's another value right here, right? This value, we'll call this theta 2. That value, so there's my theta 2, this value also has the same sign, right? Like wherever that y value is, it's the same y value. So the other answer, my theta 2, is essentially going to be pi, because that's how many degrees, or how many radians this would be, minus the thing I just called theta 1, right? So if I did pi minus the thing I called alpha A, right, I'm going to get that there's another answer. It's 2.902, right? So there are two values on the unit circle that are going to have that answer, but the calculator only gives me one, and I have to logic through the rest, right? So again, since sine is the y value, right, I use that. Sine is the y value. I use symmetry to say, hey, these two are the same y value. I need to find this value, right? And again, that's the part where knowing the domain and range is going to be helpful, because you understand that essentially arc sine or inverse sine, this measurement here, only gives me answers in this window, right? And that's great. It's fine, but I'm only going to get the answer that's over here. If I want the answers on the other side, I'm going to have to logic through them. All right, so you're going to go ahead and try the same thing. Or sorry, we'll do this one together. So we want to find when theta is the inverse tangent of 1.503. So the first thing I want you to notice is that tangent is positive, which means that I have to be looking in these two quadrants. Like I have to be looking here and here, because tangent's positive where x over y is positive. So, or I'm sorry, where y over x is positive. So either both positive or both negative. So I'm going to go ahead and do that. I'm going to go ahead and do secant tangent, right, and put 1.503 and hit enter. All right, so I'm going to get this value, right? So if you're having trouble picturing what 0.98 radians are, like this is 0 radians, and because this is pi over 2, this is like 1.5-ish. It's not actually 1.5, but it's close. So I'm going to go somewhere around here, right? I'm going to just close enough, right? So I'm going to say, hey, that's theta 1, right? And theta 1 is approximately 0.983 or 4, right? But I'm gonna store the original, right? So I'm going to store that as A. So I'm going to hit stow alpha A, right? So that's my first theta. And then here's the trick. The other spot that this is going to be the same value is the spot that's directly across the triangle, or sorry, directly across the origin from it. So basically, if I add pi, I will get the other theta. So theta 1 plus pi. So my theta 1 was approximately 0.983 or 4, right? My theta 2, which is going to have the exact same positive tangent, is going to be pi plus this value, right? The thing that I stored as A. So that means the second theta is going to be 4.125. And those are my two answers, right? So there's one, there's the other. So again, your calculator, remember that the calculator is only giving you outputs in this window, right? So this is the output of an inverse tangent, right? Is that window. I needed to find the other value that wasn't in that window. So the inverse tangent's only giving you one of those values. All right, so let's go ahead and try this one. So cosine of theta is this negative value. So I just want to point out, cosine is negative, right? Cosine is negative over here, right? So there's going to be two answers, right? The calculator, like, because this is the x on the unit circle is negative 0.861, right? There are going to be two answers. The calculator is going to give you this one, right? So this is what the output that the cosine inverse output is going to be the top half of the curve, right? It's going to look like this. So this one's going to come from your calculator, right? So we'll call that one theta 1. But this one, you're going to have to use your noggin to figure out, right? So I'm going to go ahead and find theta 1, right? So the thing I'm going to call theta 1 is the, we can just say equals because I didn't do it yet, is the inverse cosine of negative 0.861, right? So theta 1 is going to be approximately, and we'll do second cosine of negative 0.861, right? And so I get 2.6, and I didn't draw it in quite the right spot. It should be farther down here, right? It should be like, doesn't matter. It should be like closer to This is 3 point, yeah, so it should be like here, but that's fine. It should be like here and here, doesn't matter. So it doesn't really matter that you draw things to scale unless you're specifically asked to do so. It's important to know what quadrant you're in, but it's probably more like this based on, because this is like 3-point stuff, right? And this is like 1.5-ish. Again, that's not exactly right, but close, right? So 2.6 is probably somewhere in there. So this is the one I can get on a calculator. So I'm going to get 2.608, right? But I'm going to store the actual answer as A, right? Because again, I might have to use it again. And now I'm going to have to figure out the relationship. So here's my argument. My argument is that if I just went theta sub 1 this way, isn't theta sub 2, right? Wouldn't this be what happens if I went the opposite of theta sub 1, right? So essentially, if I went backwards theta sub 1, that would be like the pi over 2, which is a full circle, right? So my theta sub 2 is going to be the full circle minus the thing I just got as theta sub 1, right? So if I do 2 pi minus alpha a, oh, that's not an a, my bad, I should get that this is approximately 3.675, right? So these are my two answers, right? This guy and this guy. And you can check logically that that makes sense, right? This is about a 3.14, so sure enough, it makes sense that this is like a 3.6, right? All right. Moving on. All right, so there is no button for the inverses of the other three trig functions. So it's not super intuitive what you have to type in your calculator, but I'm going to walk you through it. I am going to point out that when you can avoid it, it's not really fun to have to do the arc cosecant or the arc secant or the arc cotangent in your calculator. So let's say I want to find the cosecant inverse of 3. I need to consider the fact that cosecant of theta would be 3, right? So if theta is the inverse cosecant of 3, then theta cosecant of theta is 3. Well, that's the same as saying 1 over the sine of theta is 3. If I solve for sine, I'm going to get that 1/3 is the sine of theta. So what I'm typing in my calculator is the inverse sine of 1/3, right? So again, if I want cosecant inverse of 3, I have to do the sine inverse of the reciprocal of that number, and then I can type it in my calculator. So I can do second sine of 1/3, and that'll give me the cosecant inverse of 3. So 0.339 or 340, depending on if you round or truncate, right? So we can kind of generalize that by saying that if I want the inverse cosecant of A, I do the inverse sine of the reciprocal of A, right? So, so this would be the reciprocal of A, right? And that's the same thing here. So again, if I want the inverse secant, I would do the inverse cosine of the reciprocal of the thing, right? So let's go ahead and try this, right? If I want the inverse secant of 4.013, then I need to type in the inverse cosine of the reciprocal of this. That's what I'm going to type in my calculator. So second cosine, right? 1 divided by 4.013, right? And hit enter, and I'm going to get that this is approximately a 1.318 or 9, depending on if I round or truncate. Again, it's worth knowing that this is what you have to write down, because I think it's somewhat counterintuitive. If I want to find the inverse cotangent, right, what I'm going to have to do is do the inverse tangent of 1 over this value. And you don't have to find 1 over that value. You can just say that's what you're doing and then type it in, right? So second tangent of 1 divided by 5.692. Close the parentheses and enter. And I get that that's about a 0.174 or 173, depending on if you round or truncate. All right, and that's it for that video.